continue with this here. In a typical problem, we'd start off, excess nitrogen, limiting hydrogen. And so how much ammonia would we produce? So we typically do grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. And if we didn't lose any, then this would be it. We get 100% yield. But sometimes we lose a little bit, so our actual yield is less, correct? This is a typical way we do it. But in this particular problem, we're going to start off with the desired actual yield. And so what we want is we want this. So we're given how much we want, and then we have to work backwards here to figure out how much we need to start with. And so we're going to have to start with a little bit extra hydrogen because we're going to lose a little bit. And it depends on our percent yield. This percent yield is 88.8, so we're going to have to start off with a lot of extra hydrogen. And so we just use dimensional analysis for this. It's 5.00 times 10 squared kilograms of ammonia. And we label this actual yield. That's how much we actually need to get. And we expect some losses, so we better start off with extra. And so we're going to go from kilograms to what? Grams. So 1,000 grams per kilogram. And then where should we go next? Where did you go? Percentage of yield. So how did you write it here?
100 grams.
Yeah, 100 grams. TY.
Over 88.8 AY.
Over 88.8 AY. Okay. So the kilograms cancel here. This gives me grams of AY. The grams of AY cancel out the grams of AY here. And that gives me grams of TY. And then once I have that, then the rest is just straight stoichiometry. So we're going to go to 1 mole of NH3 weighs 17.04 grams. Okay, the grams of ammonia cancel. And then mole to mole ratio, what is it? 3 to 2. 3 moles of hydrogen for every 2 moles of ammonia. And then we're going to use other math, which is 2.016 grams of hydrogen for every mole of hydrogen. And this is in kilograms, so we're going to go with kilograms. Yeah. So we'll just go with the same mass unit. That is, 1 kilogram is 1,000 grams. And so that'll give us kilograms of hydrogen in theory that we'll need to do this. Everything cancels out. And so what did you guys get?
99.923.
Kilograms of hydrogen? Okay. Is that what you guys got? Yeah. All right. So for sig figs, it looks like we're allowed 3 sig figs for this. So 99.9 kilograms of hydrogen. All right, so those are the 3 types of problems that we do with the percentage yield.
Okay.
We want to make this much, and we lose this much. This is how much we need. That's like when he said we know that we're going to lose 5 cookies or 5% of our cookies, so we need to make more to produce 100 cookies. It's a very long process. 500 cookies.
Okay, we'll do this. You had a question about the bonus here?
Yeah, just
Not all these I expected an answer for necessarily, but
If you put an answer like something that doesn't apply here, you're gonna mark that.
no. Chlorides, bromides, and iodides are all except for silver, lead, mercury. So this is soluble. And so, we would put WS, water soluble. Now, is it a strong electrolyte or a weak electrolyte? Or non-electrolyte? Soluble salts are strong electrolyte. So this would be a WS, water soluble strong electrolyte. SE, WS SE, water soluble strong electrolyte. This is an acid. Is it a strong acid or weak acid? Weak acid. All acids are water soluble. So this is WS, water soluble, but weak acids are not strong electrolytes. Weak acids are weak electrolytes. So this would be a WS, WE. Water soluble, weak electrolyte. It turns into a letter salad. And it's hard to keep track of. This one we don't know. Fluorides, there are a lot more exceptions for. Do you know why there are a lot more exceptions for fluorides? Yeah, they're more reactive. It's because of their size. They're a lot smaller. And so it turns out that cadmium fluoride, I think, is insoluble. But we're not going to worry about this. And so this one will skip. But we can do this one. Like that. Fluoride. Cadmium fluoride? It depends on how you define strong, weak, and non-electrolyte. There are actually two definitions for it. And so our definition, we would call it a non-electrolyte, because it's insoluble. Insoluble, well, I don't know. If you knew it was insoluble. If you didn't, ionic compounds are typically strong electrolytes, so you can call it either in this case, depending on which definition you use. And so I wouldn't, this is why I'm not being rigid on this, because if you only define it with one definition and you talk to somebody else, then, you would be on different.
So if we put down insoluble, non-electrolyte, that'd be fine.
Yeah. Insoluble, non-electrolyte, or insoluble, strong electrolyte's fine. We're out of time. And we end late today.
Can I ask a
Uh-huh.
question? If you could review, not driving force and being able to tell if something is a precipitate or when the states are saying state change.
The driving force it depends on what type of reaction there are. There are two that you need. We had three kinds of reactions. We had element, compound, combination, decomposition. And then we had double replacement and single replacement. And so the driving force is, for element plus element, we're not going to worry about driving force. So when you do an element plus element, so for example, magnesium plus nitrogen or carbon plus oxygen or whatever, we aren't going to worry about it. But for double replacements, we worry about it. Double replacements, you need to know the three driving forces: precipitation, and the only way you know the precipitation is by knowing the solubility rules. And so this is why I'm having you memorize the solubility rules. The states, you're going to get from the solubility rules. All the states are going to come from the solubility rules. And the other driving force is stronger acid, the weaker acid. Now, the stronger acid, the weaker acid, I'm asking you to memorize the 7 common strong acids, but you can kind of get them. But you're also going to have the acid chart. And so there are too many, the rankings for the acids is too much. And so you're going to have to worry about the rankings for the acids. You're going to have a chart for that. And gas formation. So you'll need to know some of the gases. Now the other driving force is for single replacement reactions. And that one you don't have to memorize. That one you're just going to use the chart to do it. Although the chart might be upside down. This chart is right side up. That's the activity series there on the top left. Our chart is upside down. But you should still be able to figure it out.
What chapter is all this in?
Chapter 19. Yeah. The activity series. The solubility rules are in the other chapter, but let me see if I have it here.
I was trying to look for it. I was having trouble finding like problems to practice it.
Okay. Chapter 19 is where you're going to find the chart. But the single replacement and double replacement is in chapter 8 and 9. Chapter 8 and 9, I think chapter 9 has the activity series. You don't have to go to chapter 19 for the test.
I'm just trying to find like problems to practice.
These are the ones we did in lab. The other practice problems are at the end of chapter 9. There are a bunch of double replacement and single replacement problems in chapter 9. We can go through specific examples if you want.
Well, yeah, we could just do a really quick example of like using all what you just talked about.
It's kind of, I mean, it's kind of hard because there are a number of examples for gas formation, for precipitation, for stronger acid, weaker. We could do like.
I was looking into chapter 9 and it talks about what you're talking about, but it's basically it's like assuming that you already know how to figure out.
Did you
It's making the assumption that you already know how to determine if something is precipitated. Like it just basically it assumes you know that already.
Yeah,
So
it's going to assume.
so where do I go back? I can't find a chapter where it actually like goes into that for that.
For
Is
precipitate.
that chapter 6?
Chapter 9 was gonna for the precipitates.
Precipitates and the gas formation, all that.
Not chapter 6. Chapter 9. So if we go back to look here, this is chapter 9 here. Okay, thanks. See you.
It talks about the strong weak acids. And then there's some problems with it. It starts talking about the precipitates, and then it doesn't tell you like, well, it says, oh well, this compound is formed, and it's just precipitate. But like, how am I supposed to know that with no prior knowledge? You know? Okay, I want to know like how to form those concepts so that I do know.
Okay, so basically what precipitates is there's solubility rules in our book here. But the solubility rules in our book here are a little bit long, so I shortened them. I'll try to bring it up again. The solubility rules, I don't remember exactly where those are, but they're in there. I think they might be in a different chapter. I have to look that up. But when you look at the solubility rules in the book, it's a bit more in depth than what I had. So did you write down the solubility rules? I wrote down.
No, I have the solubility rules. Let me see if I can find an example of. They're just if it's not telling me if something's a liquid and it just gives me a compound, and I just don't really understand how I'm supposed to just know what's a.
You aren't. You have to have the solubility rules memorized, otherwise you can't get it. So, for example, here we know that all group 1 compounds are soluble, so it's sodium, and all nitrates are soluble. And so this is going to be soluble. But over here we're forming a chloride. Chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury. So this is insoluble, so therefore you write S here, solid. Otherwise you can't. I mean.
No, I understand that, but where's the water coming from here? Like, I don't understand why it's like if there's no given
No,
water.
you're just doing a pattern, AB plus CD.
Yeah.
And so the other
I guess
thing,
I'm kind of overthinking it. I think I just don't understand. I don't understand if it gives you a question and doesn't say anything about water. It says
no, it's not water. It's an AB plus CD pattern. So it's not necessarily water. It's just water is hydrogen hydroxide. And so that's just the CD or whichever, the AC, whichever one. So here, this is AB plus CD. A is hydrogen, B is chlorine, C is sodium, D is hydroxide. So you go hydrogen hydroxide. What is hydrogen hydroxide?
That's hydro.
That's HOH. HOH is the same thing as
H2O.
H2O. That's where the water comes from. It's HOH. Hydrogen cation plus a hydroxide anion gives us HOH.
Yeah, I mean, well, that one's.
That's all it's going to come from. It's an HOH combination. The other combination is NaCl. So that's the other combination there.
Mm-hmm.
And so when you're going to get water, it's always going to be the HOH in double replacement reaction.
Yeah. Okay.
That's it.
I guess just like the aqueous thing kind of just is confusing.
Well, HOH is not, it wouldn't make sense to call HOH aqueous because
it's water.
it's water. Water dissolved in water. So that's called liquid. But all these others, if it's soluble salt, are aqueous. So that's it. I would just look at these, the precipitation, what they call the molecule formation and the gas formation reactions.
And that's all chapter 9.
Chapter 8 and 9. Yeah. It's going to be in there, but you're right. It's missing some stuff that you need to know in order to predict if it's going to precipitate.
I like my learning style is like I want to understand like the deeper what's going on.
Yeah. The book doesn't go into it as deep there.
And I think I overthink it a little bit. Like I see the aqueous thing and I'm like, okay, well, yes, I know acids are soluble, but like, are they always in water? Are they always in a solution, or is there a possibility that an acid has no water?
There's a possibility that acid has no water, but in double replacement, the acids are always going to be in water.
Okay.
Basically.
See, this is why I'm like asking these questions, because I'm like, okay, well, I'm asking all these what if
Well,
questions.
the situation in that case is to go through all the blue ones and then just look at the answer.
Mm-hmm.
Look at the problem and look at the answer, and then try the black ones.
Mm-hmm.
And so once you go through all the blue ones and then you see the kind of pattern that's going on, then see if you can figure it out. And the black ones there, and then you can ask me if it's correct.
And then the driving force is from that.
Yeah, the driving force. They break it up into 3 categories. in here, and so those are the three driving forces. They break up double replacement precipitation, double replacement, which they call molecule formation, and double replacement gas forming.
Okay.
And so that would be it.
I guess I just, maybe I haven't read through it deep enough, but I don't see anything like them using the terminology of driving force. Like I see them using double replacement, single replacement,
Yeah.
oxidation. I don't see them using the term driving force.
Yeah, they don't. That could be different, different terms, but they do have some in the homework, some reactions that don't have any driving force, and that if you predicted the products, you'd get the answer wrong, unfortunately.
Okay.
But the driving force is, you can call it whatever you want, but that's typically what it's called. It's called the thermodynamic driving force. We'll talk about later. And so it's jumping ahead. But the book, this is why if you have a chance, take a look at like a Chem 1A textbook. Maybe that's what you need, you need the book that has a little bit more depth to it.
Okay.
And then maybe it'll make sense because they're skipping a lot of stuff here. And so there's a lot of like assumed, what you said, there's a gap there. And they expect you to know it already, but it's not really discussed because they just skip it. So take a look at across the hallway over there. There's some Chem 1A textbooks over there.
Okay.
You can see what it's like. Okay.
Oh, so earlier when we were reviewing the midterm, I was a bit confused about when we were going over question 51, because I understand how you got Kelvin, but degrees Fahrenheit is the one that you.
Okay, you have to use the degrees Celsius to convert it. You don't convert it from Kelvin to Fahrenheit. You convert it from degrees Celsius to Fahrenheit.
Degrees Celsius.
Yeah. And so degrees Fahrenheit is going to equal 96 degrees Celsius plus 32 degrees. So you use this equation. So you plug in here 25 degrees Celsius.
And pretty much just mention the number.
Yeah.
That. Alright, got it.